Hello, in this video we're going to be doing 6.1 part 2. I'm going to pick up where I left off in part 1 by walking you through the process of verifying the identity in the second example that I gave you. So my goal here is to show that the left-hand side is equivalent to the right-hand side. So here I'm going to break everything down into sine and cosine on the left just so I can see my path a little bit more clearly. So I know that tangent of x is sine over cosine, and I want to show that that's equivalent to secant of x. So I can multiply now on the left-hand side my sine of x with the numerator sine of x to get sine squared x over cosine of x. Now on the left, if I want to add these two, I do need a common denominator, so I'm going to multiply the numerator by cosine of x, and I will also multiply the denominator, which is 1, by cosine of x. So this gives me cosine squared of x over cosine of x plus sine squared x over cosine of x. And that I want to show is equal to secant of x. I'm doing this because I have two different terms on the left and only one on the right, so that tells me that I should be combining these to the best of my ability. So now that I have that common denominator, I can go ahead and write this as a denominator of cosine of x, and then I have a numerator of cosine squared plus sine squared, which we know is equal to 1 by the Pythagorean identity. So this left-hand side is actually 1 over cosine of x, again because cosine squared plus sine squared is 1, and I want to show that that's equal to secant of x. Well, cosine is the reciprocal of secant, so the left side is in fact secant, which is equal to the right side, which is also secant. So I have verified the identity by manipulating only the left-hand side to show that it is equivalent to the right-hand side. In our next two examples, I've got a similar one. Here, tangent, I'm going to write as sine and cosine, so sine theta over cosine theta multiplied by cosine of theta. I want to show is equivalent to sine of theta. Now this one is fairly straightforward to manipulate. I can reduce my cosines, leaving me with sine over 1, or just sine of theta is equal to sine of theta. So I manipulated only the left-hand side to show that it is equivalent to the right-hand side. Again, in our last example, I will reduce everything to sine and cosine. So cosecant is the reciprocal of sine. So I've got sine theta times the cosine of theta, and tangent is sine theta over cosine of theta. And I want to show that that is equivalent to 1. I can reduce my cosines down to 1 and 1. So multiplying all the numerators, 1 times 1 times 1 times sine is sine. And then sine times 1 is sine. Sine over sine does reduce down to just 1, which is in fact equal to 1. So I have verified the identity by manipulating only the left-hand side to show that it is equal to the right. Now we can manipulate both sides, but I didn't need to do that in any of these cases. In all of these cases, I only needed to work on that left-hand side, manipulating it down so that it's the same as the right. But if I got stuck, I could start working on the right-hand side as well. So we've got a few more advanced identities, and these ones we are going to make use of our even and odd properties. So I'm going to go ahead and go back a few slides and check those out. So cosine is an even function because we input a negative and our cosine function doesn't change. Our sine function is odd because when I input a negative angle, I do get a negative sine function. So I'm going to make note of that when I am simplifying and verifying these identities. Cosine of a negative theta is equal to just cosine of theta. So I can go ahead and simplify the top. I've got sine being squared, but if I have a negative angle, that makes my whole sine function negative. Cosine I'm squaring. If I input a negative theta, that doesn't change my cosine, so this simplifies to just cosine theta. In the denominator, sine of negative theta becomes negative sine of my angle theta, minus, inputting a negative for cosine just leaves this as cosine theta, and I want to show that this is equivalent to cosine theta minus sine of theta. Now squaring a negative sine times negative sine is just going to give me sine squared, two negatives multiply to a positive, minus that cosine squared. In the denominator, I've got negative sine of theta minus cosine of theta, and again we want to show that that's equivalent to cosine theta minus sine of theta. Sine squared minus cosine squared is actually a difference of squares. So I can factor this like I would a difference of squares. For difference of squares, if I have something squared minus something squared, I take those two bases and I add them, and then I subtract them to factor. Well, now here, my a is actually sine, so I would have sine of theta as my first thing. And then b is my cosine, so I would add my cosine, and I would subtract my cosine. So that is my numerator of my fraction, and my denominator, I'm going to factor out a negative 1. So I take out my negative 1, and I've got sine of theta plus cosine of theta. Now I see that the sine plus cosine factor is going to reduce, which leaves me with my sine theta minus cosine theta over a negative 1. And I want to show that this is equal to cosine theta minus sine theta. So dividing this sine theta minus cosine theta by negative 1, I will get a negative sine theta and a positive cosine of theta, which I can use the commutative property to rewrite as cosine theta minus sine theta, which is equivalent to cosine theta minus sine theta, exactly as we wanted to show. So we took the left-hand side of our identity, and we manipulate it through this process to show that it is equivalent to the right-hand side. Again, we can manipulate both the left and the right if we would like, but in this case it was not necessary, as I was able to see a path going straight from the left-hand side, manipulating it to look like that right-hand side. Go ahead and take a moment to pause our video and practice this next example on your own. So I'm trying to verify that this left fraction is equivalent to sine squared of theta. So I'm going to start, since sine squared theta is not a fraction, I'm going to try and simplify this as far as I can. So I can do that by splitting up my fraction into secant squared theta over secant squared theta minus 1 over secant squared of theta. The reason I do that is because I can divide the secant squareds of theta to get 1, and I know that the reciprocal of 1 over secant squared is going to be just cosine squared of theta. And I want to show that this is equal to sine squared of theta. Now we do have a couple options here. I am going to use my Pythagorean identity, which is sine squared plus cosine squared of theta is equal to 1. I can say that I will add my sine squared theta and cosine squared theta to this left-hand side. So I added 1 to this left-hand side, which is perfectly okay as long as I do it to the right-hand side. But instead of doing it to the right-hand side as well, I am going to add 1, and I am also going to subtract 1 from the left-hand side. So I added 1 and subtracted 1, which means that I actually did nothing on that right-hand side. So on this right-hand side, I've got 1 minus cosine squared theta. I then have a plus sine squared theta plus cosine squared theta minus 1, and I want to show that that's equal to sine squared of theta. Well, negative cosine squared and positive cosine are inverses. Positive 1 and negative 1 are inverses, leaving us with just sine squared theta is equivalent to sine squared theta. So we manipulated that left-hand side to show that it is in fact the same as that right-hand side. Now we kind of already have seen factoring with trig identities, but we're going to focus a little bit more on it now. To simplify example 616, I'm going to simply just multiply this out. So you may have heard of FOIL. I just like to think of distribution. I'm going to distribute my sine to both sine and negative 1. So sine x multiplied by sine x is sine squared of x, and sine of x times negative 1 is a negative sine of x. Then I distribute my 1 to sine of x, giving me plus sine of x. And then I distribute 1 to negative 1, giving me just a negative 1. Simplifying, I can add these two terms together. They are inverses, which causes them to go away, leaving me with just sine squared of x minus 1. So I'd like to practice verifying another trig identity by using a similar process. I'm going to multiply out this left-hand side. I've got tangent squared theta multiplied by cosine squared theta. Tangent squared times 1 is just tangent squared theta. 1 times cosine squared is just cosine squared theta. And 1 times 1 is a positive 1. And I want to show that that is equal to tangent squared theta plus 2. Now tangent I can rewrite as sine squared over cosine squared, and I'm multiplying that by cosine squared. So what actually happens here is that these two things reduce, and this whole first component is just sine squared theta plus tangent squared theta plus cosine squared theta plus 1 should equal tangent squared theta plus 2. Well, now here I do see a sine squared of theta and a cosine squared of theta, so I can use my commutative property to rewrite this and put those together, and use my Pythagorean identity to say that this is just 1. And then I can simplify by combining like terms to get tangent squared of theta plus 2, which is in fact equivalent to that right-hand side tangent squared theta plus 2. So I was able to manipulate only that left-hand side to show that it is equivalent to the right-hand side of my identity. In these couple, we are going to go backwards. We are going to take an equation in standard form and factor it. So what I'm going to do first is say that I'm going to let A be equal to sine of theta. So I can factor this using substitution to make it a little bit less complicated. So I've got 2 times sine squared, or 2 times A squared, plus 3 times sine, or 3 times A, plus 1. And then we can factor. You might factor by grouping. This is my preference to factoring, but you might have your own method, so you can use whatever method you need to factor. So I have 2A plus 1, and then A plus 1. But A is actually my sine of theta, so I need to make sure I resubstitute and put back in my sine of theta, so that factored form is 2 sine theta plus 1 times sine theta plus 1. Go ahead and take a moment to pause the video and try B on your own. Here I'm going to let cosine theta be equal to A. So I've got 4 times cosine squared, or 4 times A squared minus 1. And I do recognize this as the difference of squares. So I will have 2 times A minus 1 squared. So that gives me 2A plus 1 and 2A minus 1. But then I need to resubstitute and put my cosine back in. So I've got 2 cosine theta plus 1 and 2 cosine theta minus 1. All right, that brings us to the end of section 6.1. Thanks so much for watching.